Chemistry scholars. In this video we're going to go over the Mol homework problems, and we're going to be working problems 1 through 15, just the odd numbered problems. Now before you get started, make sure you have a pencil with an eraser, a calculator, your reference tables open to the periodic table page, we'll definitely need that, and you're also going to need a blank piece of paper so that you don't try to squeeze all your work into this little bit of space. For problem number 1, it's asking us how many moles are in 71.4 grams of titanium. So we're starting with 71.4 grams of titanium, and we want moles. Now if we remember Moletown, from moles we can go to grams using the molar mass, or we can go to particles using Avogadro's number. In this case, we're starting with grams and we're trying to get to moles. So we're going to set up a conversion factor where we're going to go from grams to moles. Whatever unit we start with moves to the bottom on the conversion. So check our reference tables. The molar mass of titanium is 47.88 grams. And that's how many grams are in 1 mole. So we take our calculator. We take 71.4 times 1 over 47.88. And that equals 1.49 moles of titanium. And number 3. It wants us to determine the number of moles of arsenic in 1.90 grams of arsenic. This problem is going to work exactly the same way. So we're going to go from grams of arsenic to moles of arsenic, where 1 mole equals 74.92 grams. So we take our trusty calculator and we work that out, and you should come up with 0.025 moles of arsenic. In problem number 5, so where things get a little bit trickier. It wants us to determine the mass in grams of 5.65 times 10 to the 24th atoms of selenium. So we're starting with atoms, which is a type of particle, and we're trying to get all the way to grams. Now in the first step, we're going to move atoms to the bottom of our conversion, and we can go from atoms or particles to moles. So moles we'll put on top. Now 1 mole is Avogadro's number, 6.022 times 10 to the 23rd atoms. Keep in mind that number is right here on the front page of our reference tables. Then that brought us to moles, but we need to get all the way to mass in grams. So our next conversion, we're going to go from moles to grams. We take moles and move that to the bottom, grams on top, where 1 mole equals 78.96 grams. Then we take our calculator. In our calculator, we do 5.65 times 10 to the 24th times 1 divided by 6.022 times 10 to the 23rd times 78.96 divided by 1 equals 740.82 grams. Moving right along to problem number 7. This says determine the molar mass of silver nitrate. Well, the trick here is remembering what the heck silver nitrate is. Well, silver is a transition metal, but it always has a positive 1 charge. That's one of those things that you were just supposed to remember. And nitrate, it's a polyatomic ion, NO3. It also has a negative 1 charge, so it's just AgNO3. So now, to find its molar mass, or the mass of 1 mole of this, we take the mass of silver, which is 107.87 grams, plus we take the mass of nitrogen, 14.01 grams, plus we take the mass of oxygen, 16 grams, times 3. And we just put all that in our calculator, 107.87 plus 14.01 plus 16 times 3, and we get 169.88 grams. Problem number 9. We're blazing through this. It says calculate the mass of 42.5 moles of potassium cyanide. Well, potassium cyanide, if we remember, potassium has positive 1 charge. Cyanide is a polyatomic ion. It's Cn with a -1 charge. So that's just KCN. This wants us to go from moles to mass or grams. We can do that in one step. So we're going to go from moles to grams. 1 mole of potassium cyanide equals the mass of potassium, 39.1. Sorry about that interruption. We take 39.1 plus 12.01 for carbon plus 14.01 for nitrogen. So KCN, 65.12 grams. Now to work this out, we just take 42.5 times 65.12 divided by 1, and we get a pretty large number, 2,767.6 grams of potassium cyanide. Number 11, we're getting here to the home stretch. What mass of sodium hydroxide contains 4.58 times 10 to the 23rd formula units? Now, the thing about formula units is they're essentially the same thing as molecules or particles. Formula units is the technically correct term to use when you're talking about ionic compounds, which sodium hydroxide is. And yes, you should be able to say sodium hydroxide is NaOH at this point in the year. So now we're going to go from formula units or particles. We're trying to get to mass, which is grams. We got to go from particles to moles, and then we'll go from moles to grams. So we're going to go from formula units to moles. Put formula units on the bottom so that our units will cancel out. 1 mole is Avogadro's number, 6.022 times 10 to the 23rd formula units. But we need to keep on going. We don't want moles as our answer. We want grams as our answer. So moles will go on the bottom here. So moles will cancel. We get grams. 1 mole equals the mass of sodium, 22.99, plus the mass of oxygen, plus the mass of hydrogen, just 39.998 grams per mole. So in our calculator, we're going to put 4.58 times 10 to the 23rd times 1 divided by 6.022 times 10 to the 23rd times 39.998 divided by 1, and it equals 30.42 grams. So that's the answer to number 11. Number 13. What is the percent by mass of potassium acetate? Potassium acetate is KC2H3O2, because acetate, if you'll remember, is one of our polyatomic ions right there. It's a -1 and potassium is a +1. Now, the first thing we need to do for percent composition is figure out the total mass of this compound. So we're going to take the mass of potassium, which is 39.1, plus the mass of carbon, 12.01, times 2, because it's C2, plus the mass of hydrogen, 1.008, times 3, plus the mass of oxygen, times 2. So its molar mass is 98.144. Now we're going to need to use this number several times, so it might be to your advantage to store this in your calculator memory. So you press the store button, and we'll store it to the little variable x. Now, we're going to find the percent potassium, the percent carbon, the percent hydrogen, and the percent oxygen. For the percent potassium, we're going to take the mass of potassium off the periodic table, 39.1. We only have one potassium in this compound. We're going to divide it by 98.144, and then to turn it into an actual percentage, times 100. So we do that real quick. We take 39.1 divided by x times 100. And that gives us 39.84%. Sorry, the lights cut off on me for a second. So 39.84% potassium. For carbon, we're going to take the mass of carbon, 12.01, times 2, because there's 2 carbons, divided by the total mass, 98.144, times 100 to make it a percent. (24.47%) carbon. For hydrogen, we take the mass of hydrogen, 1.008, times 3, because there's 3 hydrogens, divided by the total mass, times 100. That equals 3.08% hydrogen, not much. And for oxygen, we'll take the mass of oxygen, 16, times 2, because there's 2 oxygens, over 98.144, times 100. (32.61%) oxygen. Now, with these problems, we can verify we did this correctly by taking these percentages, 39.84 plus 24.47 plus 3.08 plus 32.61, and they add up to 100%. So we did it right. Last but not least, number 15 says, what is the percent composition of caffeine? Boy, I wonder if anybody needs some caffeine right about now. So caffeine, C8H10N4O2. So its molar mass is going to equal the mass of carbon times 8 plus the mass of hydrogen times 10 plus the mass of nitrogen times 4 plus the mass of oxygen times 2, which is 194.2. So I'm going to go in and store that as variable x in our calculator. Now, for the percent carbon, percent hydrogen, percent nitrogen, and percent oxygen. For carbon, it's going to be the mass of carbon, 12.01 times 8 over 194.2 times 100. For hydrogen, it'll be the mass of hydrogen, 1.008 off the periodic table, times 10 over 194.2 times 100. For the mass of nitrogen, it's going to be mass of nitrogen off the periodic table, 14.01 times 4 over 194.2 times 100. And for oxygen, the mass of oxygen, 16 times 2 over 194.2 times 100. Put these in the calculator, make some quick work of this. Okay, 49.47% carbon, 5.19% hydrogen, 28.86% nitrogen, and 16.48% oxygen. So let's double check that all these add up to 100 just to make sure we did it right. And it does, so we must have done it right. Excellent.